Assalamu alaikum. How are you, my dear students? Hope you will be fine and okay. Today we have an important lecture number 30, unit 15, AC circuit. This lecture is about the AC through a pure inductance, AC through a pure inductor. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. First of all, that let me tell you that what is inductor. Inductor is the AC through inductor. You already know from the previous lecture that I told you that inductor, it is also sometimes called a choke or a coil. It is formed when a wire is wrapped around a cylindrical shape with aerated interior or any other core material such as like iron. So here you see the inductor. So inductor is a kind of, not a kind of, rather it is a solenoid, right? So that is that when you have a wire and when you wrap the wire around a cylindrical shape, so inductor is formed, and the inductor has some inductance, and the inductance of the inductor is denoted by L. It is denoted by L, and if you remember, I told you that this inductance is equal to mu naught n square L into A. So almost depends on the geometrical conditions of the inductor, such as the nature of the core material. This is the permeability of the free space, the number of turns per unit length, the length of the conductor, and its area of cross section as you see here. And I already told you in the previous lectures that inductance is measured in Henry. So here in this chapter, we will study the effect of the inductor in the AC circuit. One important point right from the beginning, which I want to tell you, is that remember that inductor, this is what you must note it down with yourself, and I just write it from the beginning, that inductor allows the flow of DC. Yeah, allow the flow of direct current, but block AC. But block AC, right? Or by the block I means resist. Okay. Now, why? This is what I will be telling to you later on, but right in the beginning, you must know this thing. So the pure inductive circuit, what is a pure inductive circuit? Pure inductive circuit. Pure inductive circuit. A pure inductive circuit is the one in which the AC source, since you know that the AC source always, when you place the ammeter or the voltmeter in a circuit, they not always measure the RMS values. So better I will write the VRMS, right? So this is our AC source. Let we say that when the voltage is established across the circuit, then from this is 0, this is T, so this is T by 2. Let we say that from 0 to T by 2, the direction of the current is this one. In the inductive circuit, we have the resistance alone connected in series with the AC source, sorry, not resistor, the inductor of inductance L. Now, let us see that we have this current, the inductive current, that is IL, or I will just label the RMS, IRMS. Now, you see that across the inductor, the voltage across the inductor is this one. That is the potential drop. And the potential drop across this inductor, I will label it as the VL. This is the voltage drop across the inductor. Now, first of all, I will like to tell you, and later on I will prove it both mathematically and physically, that why is this happen. First here, as I told in the beginning, that it allows that inductor allows AC, no sorry, allows DC but resist AC. So definitely it has some kind of resistance, and the resistance that is offered to the flow of AC current by the circuit is called the reactance of the circuit, inductive reactance. This is what we call the inductive reactance, since as I told that it resists the flow of AC. We call that inductive reactance, and that inductive reactance we denote by XL. Now the question is that why I'm doing it here is XL. Answer is simple because to differentiate it from the pure resistance R. So X is the resistance that is offered by the inductor to the flow of current. Clear? This is called the inductive reactance, and we will calculate this inductive reactance also. The second important point here, in which I will show you both mathematically and then I will explain it physically, that here the current I across the inductor lags behind the voltage. The which voltage? Remember, not the VRMS, the source voltage. The voltage across the inductor by 90° or by pi by 2. Clear? We will discuss this effect here. Now, let me this first explain to you, and then later on I will come mathematical about this. See here, look right in the beginning, that you know that we have the AC current. Once the current builds up in the circuit right in the beginning, look, there is few important point which I already told you before also. See here that look, you already know that it is not the voltage which flow. It is what? It is not the potential difference which flow. It is I, the current which flow. So potential difference only maintain the flow of current. So it will be the current which will be resisted rather than the potential difference which will be resisted, right? Just in the same way. So here we need potential difference to keep the electron moving, right? We need only to initiate potential difference to initiate the motion of the electron. We do not necessarily need it to maintain the flow of electron, right? If there is no resistance. In the same way, just your F is equal to ma. So you only need force to initiate the motion, but you do not need it necessarily to maintain the motion. So keep this point in your mind. Now, what is actually happening here in our this case, that once the voltage is maximum, that is the voltage when builds from 0 to V, that right at that time the voltage will be maximum across the inductor. Why there it will be maximum across the conductor? Because right at that time there is no opposing current flowing through the conductor, right? That once the potential difference is there, the EMF is there, which is maximum, then what happens? There is a changing induced EMF. You see that it changed both in time and polarity and magnitude. Then what happens? That when this thing happens, then there produces an induced EMF in the circuit. Now, what is the causes of that induced EMF? Because this changing current creates a changing magnetic field here, and some of the changing magnetic field lines pass through the inductor. That is what the phenomena of self-inductance occur here. Self-inductance. The phenomena of self-inductance occur, and that self-inductance produces self-induced EMF which oppose the change in the current in the circuit. This is why we say that the current lags behind the voltage here. Okay, so why? Because this induced current is in a direction opposite to the source current, right? And it resists the source current. It is just like that. It plays a role of like just the role of mass is an inertia to resist motion. So in the same way, this happens here. So this is why the voltage right at the beginning, when the voltage is maximum, right at the start, this is happening at t is equal to 0. So at t is equal to 0 here, you have the VL maximum. The voltage across the inductor is maximum, right? And the current through the inductor is 0 at that time. Now as the current builds up passing through the circuit, there produces induced EMF. And what happens, that is, as at the rise of the potential difference, the current across the inductor increases. So that is one of the physical interpretation for this. Now let us see that as we know that for the pure inductive circuit, that if we just start from the inductive circuit, as we know that, look, from the induced EMF across the inductor is from the self-inductance, rather better to write, is from the phenomena of self-inductance, phenomena of self-inductance. What we will write, that the induced EMF, this VL here in our case, that is what, in our case it is the VL. Now I will change it, okay, for you. This equals the change in current into delta T into L. Now for our this case, the potential difference across the inductor is this VL as you see it. Now look, I will write it as minus L, the inductance of this inductor, into delta I by delta T. The negative sign indicates that it is the negative sign indicates that it is the negative sign indicates that it is opposite to the source induced EMF. It is opposing according to the Lenz law. So further, what I can write, that this VL is equal, that this VL is equal to, that this VL is equal to, this VL is equal to minus L into delta by delta T into delta into I. Now for the AC circuit, what is this I? It is I max into sine omega t, right? By taking the limiting value VL, what we can write, that minus L into the minus L into this Im, it is constant since it is a maximum value, Im into minus Im into the limit. I will set a limit for this, that this delta by delta t equals sine omega t. So here the limit of this, when delta t tends to 0, this is just like this. When delta t tends to 0, the sine omega t is equal minus cos omega t. Sorry, minus cos omega t. We will write it here. Okay, so this is what you will learn in mathematics. So for the bio student, you need to remember this statement by heart because I cannot take you into a deeper mathematics. So this VL equals minus omega L I M into cos omega t, right? And rather one step I should increase for you, minus L I M, and here what I'll be writing, this is sorry, this is minus omega. Okay, it will be taken out from this sign. Outside is a coefficient and it will be replaced by cos omega t. So minus omega cos omega t, right? And then this will become VL. It will become minus L omega Im into cos omega t. It will become this. Now let us see that, look, this is simple mathematical function as you see. This will become plus a simple mathematical function. So here what you see, that look, here you see that this Im, okay, and this is what, this is the V. So look, this is the L omega Im is in fact a constant with us. Okay, now if I write it like this, instead of this, I can write it as, look, this whole, that it is nothing but this constant is equal to V max. It is equal to what? To the V maximum velocity. So, sorry, not the maximum potential difference. I'm so sorry. So here what I can write, that this VL is equal to what? The Vm into the sine into, if I just replace this, because you know that cos theta is always equal to sine of theta plus pi by 2. It is a mathematical identity. So instead of this, what I will write here, that I will write it like the Vm into sine omega t plus pi by 2. Plus what? Plus pi by 2. So this is one equation here. Right now also, let if I write, as you see, look, if I replace this whole equation, the Im into the cos omega t, then what you see here, that equation will become what? It will become the VL into what? The VL into the R. Let us simple say here, look, what is this? This will definitely cause the IRMS. It will cause what? The IRMS, this. So what does this mathematically? Here mathematically, this shows that VL leads VL leads I, because you know that what will happen, Vm, this is what, this is sinusoidal voltage and it will cause a sinusoidal current. It leads the IRMS by pi by 2, by 90 degree. So that is why I told you that later on I'll be explaining this thing to you. Is it clear? Now let us going back to the equation number. Let I label it as equation number 1. So from equation number 1 again, from equation 1, what I can write, that this VL equals L omega into Im into cos omega t, cos omega t. Now, as I told that, look, what I can write here, that this, from this equation, I can just simply write that as I told to you that this is yes, okay. This will be equal to what? This will be equal to the VL by IM. This will be equal to what? It will be equal to LW into cos omega t. So definitely, if you look to this part of the equation, see here, then this part of the equation, look, this is as from Ohm law, what we say, V is equal to IR. So what is V by I? It is definitely R. So here there is no pure resistor, but here it is inductance. So definitely what will happen, that since it is a mathematical function, this one, so it has no specific unit. So definitely this LW will be equal to some sort of resistance, L omega resistance. And what is that resistance? We call it inductive resistance, inductive reactance. That is called what? The inductive reactance. And then definitely this inductive reactance will be denoted by XL, and it will be equal L omega, right? Now, what does this means? That the resistance that is offered to the flow of current by the inductor is of this value. And this is why, now let me again move one step further, that this inductive reactance is directly proportional to the inductance. Greater the inductance, greater will be the opposing power. Smaller the inductance, smaller will be the opposing power. And it is directly proportional to the angular frequency also. So instead of this omega L, I will write R, I will write 2 pi F into L. So here it shows that XL, that the XL is directly proportional to F and XL directly proportional to L. Now look, this is why I told that in it it allow the flow of AC current, where because their reactive, and for the DC circuit it's reactive inductive reactance is 0. Why? DC has frequency 0, so XL is 0, therefore it allows there. But here the AC has a frequency and the inductor has inductance, and therefore you have the resistance here, and this is why it opposes here. And similarly, this is the diagram for it. If this is the VL, here the VL lead, so you have the VL here and you have the IRMS here, yeah, the IM here. Okay, so this is called the phasor diagram, and that is the phasor diagram for it. The V and the Z phasor is not here, sorry. This could be done in the RLC series circuit. The V phasor is enough for you here. Okay, or this is, you may say that the VRMS, and we have that as the VL. Okay, so and for the Z, that is also AZ. For the Z, we have this the XL, but we don't have the resistance here, so fine, it is enough for that. Now, the next important point here is the power loss in inductor. The power loss in inductor. The power loss in the inductor, power loss is 0. The power loss in pure inductive circuit is 0. What does this mean? That like the resistor, it does not dissipate the energy in the form of what? In the form of heat. Therefore, it is used, what? It is used to store that energy, used to store energy. It control the flow of current in the circuit by storing the energy. And this electrical energy is stored in the form of magnetic field. In the form of what? Magnetic energy or magnetic field. Magnetic field. Like that. And whenever the circuit needs it, it returns it back. So you see how we can calculate the power loss. Look, A is for the power expression is we know that power is equal to what? As that power is equal to the IV average value. During the first half cycle, the voltage is positive and the current is negative. Therefore, what happens? Therefore, the power supplied is what? Therefore, the power supplied is negative. The power supplied is what? The power supplied here is negative. The power supplied is what? But okay, let us see. Look at this diagram only. Clear? So, in the voltage, yes. Since there is lag and lead, so the for the for the pure inductive circuit, the first half, that is during the first 90 degree of the cycle, the voltage is positive and the current is negative. Therefore, the power is what? The power loss is negative. The power what? The power loss is negative. This means that power is flowing from the coil to the source. Negative power, as I told, negative power, that the power or the energy is flowing from the coil to the source. During the next half cycle, both voltage and current are positive and the power supplied is positive. Therefore, the power flow from the source to the coil, it is positive, so power will flow from the source to the coil, which you can see here in this diagram. Is it clear? So look now, if we want to calculate this in a simple way, that power equals this is the V, here I will be writing the Im into sine omega t into the Vm into the sine omega t, like this. So here for Im and Vm, and here the sine omega t, and here you have the cos omega t, right? So what is the sine omega t average value, and the cos omega t average value is 0. Now that is very simple. Just forget all those top sort of explanation, but the very simple thing here is that look, when I is maximum, look why the power is, that is why we put it 0, I m and v m 0. The answer is simple, that when I is maximum across the conductor, at that time VL is 0. This is rather VL. The VL is 0. When the VL is maximum, then I is 0. So they do not attain their maximum and minimum values simultaneously. Therefore, in the pure inductive circuit, power loss is 0. In pure inductive circuit, the power loss is 0. The power loss is 0. Okay, that is the simple sort of explanation. That is the now in the application, as I told you, that it can be used as a choke coil application, right? This can be used in many electrical circuit, but here it can be used as the choke coil A choke coil is a solenoid or inductor used in a circuit that which offers a high reactance to the frequency at a certain frequency range without limiting the flow of current. So this is used to control the power surge in the circuit, right? That is, the inductor is used for the controlling of the current in the circuit. The inductor controlling controlling current or power surge. This is used in tuning circuit to select the desired frequency and reject the unwanted. This inductor is used in the AC filters, AC filters, right? Circuit, yeah, in the filter circuit. When you convert AC into DC, so this is the circuit. In that circuit, the inductor is used to remove the smallest possible AC frequencies that exist there. Okay, so this is used to prevent electrical signal along the undesired path. Okay, so that is the, so these are the applications of the AC circuit. So thank you very much. Inshallah, see you in the next lecture.